pause the recording. So there's going to be a lot of dead time at the end of that recording. All right, so let's look at some of these other problems here. And so the yield, they're sacrificing the yield for speed. You know, that's okay if the yield is lower, if they produce it faster but if they want to maximize the yield, they should do it at lower temperatures. Although 200 degrees C doesn't seem so low. It's all relative, you know. So if you get it too cold, then things don't move. And so the higher temperatures are used to speed the reaction rate to an acceptable level. Lower pressure is dictated by limits of mechanical design and safety. All right. Calcium hydroxide, we classified that as soluble, but it's really borderline, you know. But is much more soluble than most of the other ionic compounds that are similarly classified. It's KSP. The KSP is going to tell you is KSP and solubility are related. Ka and pH are related. That's all the take-home message we have here. We can do different calculations, equilibrium style calculations for those. This is combustion of ammonia to produce nitrogen dioxide. So we can produce nitrogen monoxide or nitrogen dioxide depending on the conditions we have here. And so this is at equilibrium. So if we add NO2, it's going to shift it left. That's product. If we reduce temperature, this is exothermic. So if we reduce temperature, we're removing heat. We remove heat, then it shifts it to the right. We add nitrogen. If we add nitrogen, it has no impact here because nitrogen does not participate in this equilibrium at all. So we could add plenty of nitrogen. We could add like 1,000 PSI of nitrogen. That's not going to make any difference to this here. However, ammonia will. If we remove ammonia, ammonia is a reactant. So if we remove ammonia, it shifts it to the left to compensate for it. Add a catalyst, both reactions are sped up. Some systems at equilibrium are exothermic and some are endothermic. Is this statement always true, sometimes true, or never true? Actually, some systems at equilibrium are exothermic and some are endothermic. I don't understand this question. So the truth of the statement depends on how you interpret it. A system at equilibrium is neither endothermic nor exothermic. The system is closed. Yeah, that's why I didn't understand it. But the reaction could be, you know, in one direction or the other direction. So the forward direction is, so it depends on how you interpret it. That makes sense. But that question I don't like, so let's skip that. 89, the equilibrium constant K can have many values for any equilibrium. No. For an equilibrium, the temperature, if you change the temperature, then it's going to change K. But if you leave the temperature alone, then K is going to be the same for a particular equilibrium. I think that's what they're saying. Temperature affects reaction rates in forward and reverse directions differently. Therefore, the value of the equilibrium constant depends on temperature. Change the temperature, the value of K changes. An all gas phase equilibrium can be reached between sulfur dioxide and oxygen on one side of the equation and sulfur trioxide on the other. Write the two equilibrium constants. So we got to just write the equation and write the equilibrium constant. So we write the equation, write the equilibrium constant. Hard water has a high concentration of calcium and magnesium ions. Focusing on the calcium ion, a common home water softening process is based on a reversible chemical change that's expressed by this. ZE. What is ZE? Zeolite. Represents a solid resin that is an ionic compound between sodium ions and zeolite ions. Just a moment. Zeolites are these ceramic-like materials. Zeolites are common in industrial things. For the lab I used to work next to, they specialized in zeolites, and one of the zeolites that they used was a zeolite that catalyzes or helps convert methanol into gasoline. And so this is a project that they're working on. But zeolites can do other things too. It's these ceramic materials that do, then they have these channels and other stuff. A complex arrangement of silicate and aluminate groups. You know, silicate is SiO4 or SiO2, illuminates the Al2O3 type groups. They're tetrahedral groups for silicon, and aluminum is a little bit different. Calcium zeolite is corresponding calcium compound. When during the day is, okay. So they're just looking at this. This is what a zeolite looks like. It has all these channels. And so this is ceramic that has these channels, and it causes them to do interesting reactions. You know, the zeolite that converts methanol into gasoline is called ZSM5. 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 Let's look at ZSM5. Zeolite gasoline. In 1977, ExxonMobil developed MTG based on ZSM5 zeolite catalyst. When contacting ZSM5 zeolite, methanol is converted into hydrocarbons that are limited in fractions, similar to traditional gasoline. So this, you know, this was a way to make synthetic gasoline, you know, starting with methanol. Methanol you can generate fermenting wood. This is called wood alcohol. And so you could use wood alcohol and use that to convert it to gasoline. This was in 1977, but they don't really make that much. Methanol is not so cheap, you know. Methanol is kind of pricey. But the silicate to aluminate ratios change. You know, the structure of this. Methanol to gasoline over zeolite, ZSM5, improved catalyst performance by treatment with HF. Okay. Well, this feels like gasoline, methanol, ethanol, hydrogen, you know, and so trying to think of less expensive ways, you know, to make fuels, and one way is to use solar, you know, solar cells generating. So that's another thing. The ZSM5 lab was down the hall from mine, and then another lab, which was on the other side, they were looking at using photovoltaics to electrolyze water to form oxygen and hydrogen. Actually, they were really only interested in hydrogen. And so rather than using the water gas shift reaction, which is taking carbon monoxide and reacting with steam, very expensive process. If you use solar energy to generate hydrogen, that would be much, much cheaper. Except the conversion efficiencies were kind of low. And so that's, you know, I chat with these guys about their research when you work on the same, you know, floor of the building. And so I don't know the latest information. This is old stuff. This ZSM5 is old stuff. But what we're looking at is, okay, if we use solar energy, that's what we call electrochemistry. And so that's the last chapter. We're not going to talk about nuclear chemistry, although nuclear chemistry is very interesting. We're going to just talk about redox, electrochem. Redox. This is the classic lemon battery here. And so you can make a lemon battery out of pennies. For example, if you have a penny, the penny is copper coated. And so you stick a penny in here, which is copper. And then you take the other piece and you scrape off the copper coating. When you scrape off the copper coating, you have zinc underneath the copper. And so this is zinc. So if we put copper and zinc into a lemon like this, we can generate a voltage. Now, doing one like this will generate a certain amount, but if we do two in series, one after the other, then it can generate a little higher voltage. I don't know how much voltage you need to run this clock. There's probably a certain minimum, but this only generates about 1 volt. And so if you need about 2 volts, then you'll need 2 of these. And that generates about 2 volts if they're connected in series. If you need 3 volts, then you stick in 3 of these and you'll get about 3 volts. And so you can do it that way. So in this chapter, we're going to be looking at redox, to generate electricity, and using electricity to generate chemical reactions. We could use electricity generated by solar voltaics to generate the reaction, generating hydrogen gas, photovoltaic cell. And so redox, we already talked about electron transfer reactions, here, but we didn't talk about it in the context of generating electricity. So here we're going to talk about it in the context of generating electricity. And so this is this is a battery here, essentially. This is a redox reaction that will generate electricity here. The way we generate electricity is this. Normally when copper and zinc react, they react directly. And so if I take copper ions and zinc, they'll react with one another, dissolving zinc and copper 2 sulfate. That's 5 minutes long. Let's find a short one. Here. This is short. This is only 1 minute long. Watch that and see. I got to get rid of the no ads. Good.
Redox reactions are spontaneous in only one direction. Here we have an example of one spontaneous and one non-spontaneous redox reaction. First, we have the reaction of zinc metal with copper ions, then the reaction of copper metal with zinc ions. Let's see which one is spontaneous. You can see the zinc metal turned dark due to the formation of solid copper on the surface. For the zinc and copper metal reaction, there was no reaction.
Spontaneous just means that there's a driving force. So spontaneous reactions have a driving force. Non-spontaneous reactions, there's no driving force. So normally the copper, in that particular reaction, they just went ahead and put the zinc right into the copper. And so they had a beaker, and in this beaker they had copper 2 ions. And copper 2 ions are a good oxidizer. They probably had copper 2 sulfate. Sulfate's a good oxidizer too. But in order for sulfate to be a good oxidizer, we need H+, and there's no acid in here. There is a little bit from the water, but not enough to make the sulfate the better oxidizer. So copper 2 is the better oxidizer. And then you stick in this piece of zinc. And zinc is a good reducer. Zinc is used a lot as a reducer, because it's inexpensive and it's easy to take the electrons from. So copper 2 is going to take the electrons straight from the zinc and precipitate out copper metal. And so the copper 2 takes the electrons straight from zinc to precipitate out zinc metal. And so these 2 electrons come from, to precipitate out copper metal. So where did these 2 electrons come from? Those 2 electrons came from the zinc directly. So the zinc gave up 2 electrons in the process forming zinc ions. These zinc ions go into solution, so that's aqueous. And the zinc metal is going to be eaten away. And so eventually that zinc is going to disappear as long as copper is the excess reagent. Pretty soon the color is going to go from blue to colorless because zinc ions are colorless. And so we see electrons are transferred. But in this case, the electrons are transferred directly. The copper is going to attack the zinc directly. Now, the way this is designed is we put the copper in one beaker and the zinc in another beaker. And then we have the copper 2 pull the electrons off the zinc in the other beaker. But how do you get the copper 2 to pull the electrons off the zinc in the other beaker? We take advantage of metals. Metals are a sea of electrons here. And so what copper 2 is going to do is it's going to try to take electrons from copper metal. It's going to be unsuccessful because it's going to be a tie. Copper 2 versus copper will result in a tie. And so copper 2 is trying to take the electrons, but metals are an ocean of electrons. And so this little current here, you know, this pulling of the electrons, it's pulling the electrons. So that's going to, that little tug there is going to be felt throughout the entire stick. This stick of copper is called an electrode. And so then this entire chunk of copper, the electrons are being felt. So we have a chain or a train of electrons. And so this electron gets pulled, which pulls this one, which pulls this one. And then this electrode is connected to a piece of copper wire. This is copper wire. And so again, copper 2 is not going to successfully oxidize copper wire, but copper wire also has an ocean of electrons. And so this copper wire is going to hit a piece of tungsten wire. Tungsten wire also has an ocean of electrons. And then it's going to hit a piece of copper wire again. And then it's finally going to hit the zinc. And so this electron chain extends all the way. And so here is how they're connected. They're connected by the wire. So as the copper ions are pulling on the electrons here, that pull's felt all the way over here. Now, once it hits zinc, then copper 2 is strong enough to oxidize zinc. But in this case, we can't form zinc in air. You know, zinc ions in air would be too unstable. We need to form zinc ions in water. Zinc ions in water, the water will stabilize it by forming a hydration sphere. Whereas if we form zinc up here, it's not going to happen because zinc 2+ in air is too unstable. So that doesn't happen. Whereas zinc 2+ in water is a lot more stable down here. And so in this way, even though the oxidizer is way over here, you know, here's the oxidizer. The oxidizer is going to be able to reduce something way over here via remote control, except the remote control is not wireless. The remote control is via wire here. So there's a piece of wire. And those electrons are going to be connected all the way down through here. And so once it hits the zinc, we have the sea of electrons. So eventually we're going to find the weakest link. Now the weakest link are usually on the corners or the edges. So you can see, do you see the corners here and the edges are being quite corroded? And so those are usually the weakest. And so if they're cracks, corners, chips, those are going to be eaten away first. And so it's starting to eat away on the corner. Probably the corner here is probably the weakest. The corner of zinc is the weakest because it's held on with fewer bonds. So if we look at a corner atom at the very corner of this electrode, it's stuck right at the corner here. And so this will be the weakest. This will be the first to go. It's like a sugar cube. When you dissolve the sugar cube, you're going to surround the corners first. and then the edges. The edges are the next to go after the corners. After the corners have been rounded, the edges will start to go. And then the atoms on the surfaces are the last to go on the surface, and the atoms inside are the last. The atoms inside are the most stable. And so these are the, what do you call them? The most outlying zincs. So those are the weak links. And so, you know, the electrons, the sea of electrons is being pulled on, and eventually you'll hit a weak link. The weak link is right at the corner here. And boom, you'll take those 2 electrons. Those 2 electrons are going to go all the way over here. Now, they aren't literally going to be these 2 electrons. The copper is just going to eat 2 electrons, and the chain's going to shift 2 electrons more. And we're going to deposit copper solid here. Well, when you have a flow of electrons like that, that's called electricity. And so this is using redox reaction to generate electricity. Well, we call that a battery. And so this is a battery. A battery is using chemical reaction like this to generate electricity. I didn't start off with chapter 19 talking about this because I didn't want to talk about batteries first and then redox reactions. I just want to talk about the reactions alone. Okay. Here. Now, I said zinc in air is not very stable, zinc ions in air. Zinc ions aqueous are a lot more stable because they can be solvated or hydrated, and that'll stabilize them by forming ion dipole type attractions. Now, it's, yeah, the water is going to help, but it doesn't help enough. And so what's going to happen is pretty soon you're going to generate too much static electricity, and the electrons will stop flowing. Like, for example, if we build up too many zinc ions in here, this is becoming hugely positive. And we're going to generate a huge voltage, and that huge voltage can result in sparks or just stop. And in fact, in this case, it's just going to stop moving electrons because it's going to get harder to pull the electrons through. You know, you got too many positives out here trying to prevent that. And so to reduce this positive charge over here, we need something to help neutralize it. Water helps, but not enough because water is only partially negative. Well, we need our full negative charges. So we look for something that's not going to react with zinc. Well, sulfate won't react with zinc because sulfates are soluble, except for silver, which is asterisk, lead, mercury, calcium, strontium, barium. So zinc it's not going to react with. So sulfate's a good candidate here. So if sulfate comes in here, that will help neutralize what we call the space charge, the static electricity. So we need sulfate to come here to neutralize the static electricity that's being generated here. Otherwise, the electrons will stop flowing. And the same thing over here is the copper 2, we're losing copper 2, so we're losing positive charge. There's sulfates already in here. And the sulfates are looking for a cation. Well, the copper 2's disappeared. And so what we have to have is we have to have 2 potassiums for every sulfate. In other words, we'll have to have 2 potassiums for every copper 2 that plates out on this chunk of metal. And so where are we going to get that? Well, it doesn't have to be potassium. It just has to be something that it won't react with. And so in this case, potassium sulfate. So this is called a potassium sulfate salt bridge, and it's just an aqueous solution or gel of ions. And this could, the sole purpose of this is to neutralize the static electricity, to neutralize the space charges, because generating too much negative charge over here because we're losing positive charge is going to be a problem, and generating too much positive charge over here is going to be a problem. And so we can neutralize that by adding anions over here and cations over here. And so these are electrodes. There are 2 types of electrodes. One electrode is called the cathode. The cathode is where the cations go. The other electrode is called the anode. The anode is where the anions, sulfates and anions going to go. And so anions travel to, cathodes, cations travel to eliminate the space charge. And so without the salt bridge here, there's no electricity. This light bulb would not light up. if we put the salt bridge there, then we can get it to light up. This is only going to generate about 1 volt, so it's probably going to be pretty dim. Like LEDs, we need about 3 volts to light up an LED. And so if you're doing a lemon, you're going to need 3 zinc pennies and 3 copper pennies. Then you probably can light up an LED. Let's see here. Okay, so this is the basics of a battery. And so this is called the cathode compartment here. This is the anode compartment. So at the cathode compartment, we have the oxidizer. And so the job of the cathode is to feed electrons to the oxidizer. That's the job of the cathode, is to feed. Well, if its only job is to feed electrons, then any electrical conductor will work as long as it doesn't react directly with copper-2. And so what we need is, at the cathode, we need an inert electrode. One of the most common inert electrodes are two. Two of the most common are platinum and gold. Gold and platinum are the 2 most common inert electrodes, and these electrodes will feed electrons to the oxidizer without being attacked. Copper is good, except, you know, copper gets tarnished, copper gets oxidized, which lowers its efficiency. Another one that's quite common is graphite. Because all these conduct electrons, so they conduct electricity, therefore they can feed electrons to copper-2 ions. That's it. However, when we look at the anode is not inert here. This is a reactive anode. In fact, the anode is going to be supplying the electrons. The electrons are going to come from the anode, and in the process, zinc metal is going to be oxidized to zinc 2 plus aqueous. The zinc 2 plus aqueous will be okay for a moment, but it's really going to need some sulfate, some anions. It doesn't have to be sulfate, it could be chloride or whatever else that doesn't react with zinc 2. And so this is reactive. And so what we have here is the oxidizers here, in the reducer is the anode. This is the reducer. And so zinc is our reducer here. Now, our reducer is supplying the electrons. This supplies electrons. And so we have this sign here. The anode is negative. And so the electrons originate at the anode here and then travel, they're consumed at the cathode. And so the cathode is pulling in the electrons. The anode is generating the electrons. So the cathode pulls in the electrons because the copper-2 ions are pulling on the electrons. So the cathode gets a positive charge. The anode gets a negative charge. So this is the basics of a battery, you know. These are called half reactions, and these are just like on the chart, you know. Here's your oxidizer. Oxidizer is taking 2 electrons. Here's your reducer. Reducer is giving up 2 electrons. Then we have the net redox reaction. The net redox reaction is shown here. Here. The electrons we don't really see. I mean, those are going through the wire. But, there we go. Copper-2 is being, what we say is reduced. There's something called oil rig. You know, the oxidizer is reduced. Oil rig. Oil stands for oxidation is loss. So oxidation is loss. Oxidation means you're losing electrons. Rig, reduction, is gain. And so copper-2 is gaining electrons. Therefore, copper-2 is being reduced. And so we call this reduction. And what happens is the oxidizer is reduced. The oxidizer takes electrons, therefore being reduced in the process. Reduction is gain of electrons. Over here, the zinc is undergoing oxidation. Zinc is losing electrons. So oxidation is loss of electrons. And so this is a process of oxidation here. What gets oxidized? The reducer gets oxidized. The reducer supplies the electrons. So the reducer gets oxidized, supplying the electrons. So that's oil rig there. Here's the reaction, but this is direct reaction here. We're not going to generate any electricity because electrons are being transferred directly to the copper 2. Copper 2 is attacking the zinc. Here. This is a chunk of iron in acid, and the acid is attacking. Is this bromine? No, this is acid, hydrochloric acid. It's a redox reaction. The acid is taking the electrons, iron's losing the electrons. Bubbles of hydrogen gas are forming. That's not a cell, I mean a battery. Batteries we give another name for. Batteries we call voltaic cells. Voltaic. Voltaic cells and galvanic cells are the same thing. So these are the same, voltaic and galvanic cells. These are going to generate electricity. However, electrolytic cells do not generate electricity. Electrolytic cells consume electricity. And so these use electricity to drive non-spontaneous reactions. Use electricity to drive non-spontaneous. Non-spontaneous means there's no driving force. And so, yes, redox reactions. So we could have some redox reaction that doesn't normally occur, like water. You know, water normally doesn't decompose into hydrogen gas and oxygen gas, but we can use electricity to force it to. And when we use electricity, we have to design an apparatus, the electrolytic cell. If we design a battery, then we're designing a voltaic cell or galvanic cell. So the battery we just looked at is a voltaic cell / galvanic cell, same thing. Describe and identify the parts of an electrolytic or galvanic voltaic cell. And so these are two different cells. And explain how it operates. They're two different cells. We need more examples, you know, we need more examples to look at. This system is an example of a voltaic cell, sometimes called a galvanic cell. So figure 19-1. This is the figure we were just looking at. That's the voltaic or galvanic cell. Here they're adding some few more details. You know, rather than a light bulb, they put something called a voltmeter there, and they can measure. Volts are the kind of the pressure on the electrons to transfer there. And so here's a more detailed figure showing how the voltaic cell operates. This is the same battery we were looking at. However, I didn't put in the concentrations. Here they have the concentrations. Here they're using copper, which is fine. That's our inert electrode here. Here they're using zinc. Okay, we need the zinc. The zinc is going to react. And there's sulfate present here. But even though there's sulfate present, Here, there's not enough sulfate because we're going to continually generate more and more zinc. At the same time, we're not generating more sulfate, and therefore the sulfate has to be added there from the salt bridge. Over here, the copper-2 ions are being consumed, and there's already sulfates there. There's a fixed amount of sulfate, and therefore we have to add some cations there, the potassiums. They didn't balance this, but it doesn't matter. Okay, so electrons want to travel left to right here. So we make sure the polarity of the voltmeter is set up right. And so the electrons are being pulled through this at 1.1 volts, positive end of the battery. Let's check this out.
In a voltaic electrochemical cell, an oxidation occurs at an electrode called the anode. The electrons released at the anode travel through a wire to another electrode called the cathode, where the electrons are consumed in a reduction reaction. Anions are then shuttled through a salt bridge from the cathode compartment to the anode compartment. Otherwise, a net negative charge would build up in the cathode compartment. The negative charges move in a circuit through the cell.
There's some more examples of battery, nickel-cadmium battery. Let's take a look at the diagram. This is a rechargeable battery.
In a rechargeable nickel-cadmium battery, cadmium is oxidized at the anode to form cadmium hydroxide under alkaline conditions. The electrons are used at the cathode to reduce nickel from the +3 oxidation state to the +2 state. The products of each half reaction adhere to the electrode surfaces. Application of an external current to the battery can reverse the reactions, oxidizing the nickel back to the +3 state, while reducing the cadmium hydroxide to metallic cadmium.
So basically, in a spontaneous cell, the electrons want to travel. And so here, the electrons want to travel left to right. If I want to recharge this battery, I got to force the electrons to go backwards. So I put a power supply here and then just force the electrons to go backwards. If the reactions are reversible, then it'll recharge it. If the reactions are irreversible or very difficult to reverse, then it won't recharge it. And so we have two types of batteries like in that sense. We have the primary batteries, which aren't rechargeable, and the secondary batteries. Secondary batteries are rechargeable. So this would be an example of rechargeable battery. Lithium batteries are primary This one is primary battery, it looks like. Actually, they aren't all primary batteries. There are a lot of lithium batteries that are secondary batteries as well, like on laptops and whatnot. Car batteries, secondary battery, but in this case, they're using car battery to force the electrons to go backwards. And so here they're forcing electrons to go backwards, in this case. This is, when we force electrons to go backwards by using a power supply, it could be like a battery or it could be electrical power supply. We call it electrolysis, using electrons. Now, what's happening is the electrons are being forced, and so they'll reduce whatever they can reduce. So in this case, they're reducing sodium ions. This is molten sodium chloride. You see NaCl liquid. So they have to put some kind of heat down here. And then if the battery is pulling electrons here, it's going to force oxidation to occur, and they're oxidizing chloride here. And so the battery is acting as an oxidizer, oxidizing agent. It's going to oxidize something, chloride, and it's also acting as a reducer. It's pushing electrons to sodium here. And so sodium chloride is stable, but sodium metal and chlorine gas aren't. And so there's got to be a barrier. So they put a barrier here to separate it. This is one beaker. This is not a 2-beaker setup. It's just 1 beaker setup. But we got to just keep the sodium from touching the chlorine. Otherwise, we have a potential explosion could occur. So it's electrolytic setup there. Here's another electrolytic setup. But here, they're using graphite electrodes here. You can tell. These are graphite rods. They're getting very hot, it looks like. They're glowing. this case, because the burner, this is a crucible. This is called a, well, actually, this is not a crucible. This is called an evaporating dish. So they're doing this in a ceramic. This is, this ceramics is usually aluminum oxide, but aluminum oxide is difficult to work. And so this is aluminum oxide mixed with various other cations to make it easier to shape and do that kind of stuff. But it makes it more reactive. If you have just pure aluminum oxide, then it's very unreactive because aluminum oxide is quite a stable lattice. And so I had, it's like sapphire. Sapphire is just pure aluminum oxide. So I had sapphire crucibles, I had sapphire beakers, I had sapphire, a whole bunch of stuff made out of solid sapphire. And it's expensive. And so you just get a porcelain one like this, is a lot cheaper. Anyway, this looks like they're melting a salt and then electrolyzing it. And this looks like they're melting. I tried melting sodium chloride. It's hard to melt. And so they have molten sodium chloride here. And then they're going to force electrons on the sodium ions to create sodium atoms. And they're going to pull electrons off chloride to form chlorine. So this is going to generate sodium metal and chlorine. Sodium metal at these temperatures is liquid. Okay. Electroplating is another use of electrolysis here. They can electroplate gold on other metals. Are the batteries used to power portable MP3 players best classified as electrolytic, voltaic, or galvanic cells? Voltaic, galvanic, you know, these require a battery. Electrolytic, you're trying to cause a chemical reaction to occur. And so voltaic or galvanic is it. Oxidation numbers and redox reactions. So that's a little bit about batteries, you know, here. Since I think that's it for batteries, let's take a look at solar voltaic hydrogen generation. I don't think I need a generator here. So let's see a recent article. The most common method is solar-based is to use photovoltaic cells. Scholarly paper, assessment of hydrogen energy for sustainable development. That's, yeah, a lot of people are very interested in this because this is making hydrogen infrastructure. Right now, there are a couple of hydrogen fueling stations in Torrance around here, and there's hydrogen cars. You know, Toyota had one. I was thinking about getting it. I talked to one guy. I talked to the Spartan guy. One of the guys at Spartan got a hydrogen fuel cell car. And so the car uses hydrogen and oxygen to generate electricity. With a fuel cell, it's like, fuel cells are a little bit different because in a battery, you have a fixed amount of fuel. And so the fixed amount of fuel is inside the battery. So you have bigger batteries like a D cell that has more fuel, and a smaller battery like a AAA, the same reaction, you use the same voltage. Just the D cell has more fuel, so it lasts longer. But it's still a fixed amount of fuel because once you run out of the fuel, or you know the voltage drops below a certain point, you throw it away. Well, you aren't going to be able to do that with a car. Like, you know, okay, you have a battery in a car, what do you do? Well, one thing you could do is recharge it, but, you know, recharging it, you just bring it home and plug it in. Another thing you could do with that battery is you can just add more fuel to the battery. And so that's the whole idea of hydrogen fuel cells. You know, you have the reducer, which is hydrogen, and the oxidizer is air. So you're not going to run out of air unless something catastrophic happens, and then we're all dead. But the hydrogen, you're going to run out of the fuel. And so they have these hydrogen fueling stations all over. Hydrogen is also a very dangerous gas because it is a good reducer. So you got to be careful. But how do you make the hydrogen? And so we've got to make it cheaply. you know, to make that work. And so let's look at hydrogen generation from water using solar energy. This is cited by 1,642 people. This is a review article. Review articles are good if you want to just get started. And oh wow, this is the whole article, which is pretty good because usually they make you pay for an article like 30 bucks or something, unless your school has a subscription, which our school doesn't have a subscription to a lot of scientific journals. But this is nice. A Elsevier, they usually charge for this. So we read the abstract, you know, the abstract will give us a quick synopsis of the whole thing. High efficiency photoelectrochemical cells. When was this published? This is old already. This is 2002. So this is not the latest cutting edge. That's probably why it's free. You know, the technology's changed quite a lot since then. Let's see if they have some diagrams of some cells. Yeah. And so here's the photovoltaic cell here, which is going to generate electricity. So it's going to force electrons to go backwards. So electrons are traveling. By convention, normally, and you don't have to write it like this, but in a voltaic cell, we have the electrons going left to right. In electrolytic cells, I try to do the opposite. I try to be consistent, so it's always the same, so it's easier to remember, you know. And so when I do electrolytic cells in general chemistry, I always have the electrons go right to left. And so here it's going to reduce. It's going to reduce the hydrogen to hydrogen gas. So here, hydrogen ions actually get reduced to hydrogen gas. But the hydrogen, this is a little bit of misconception because it's water. Actually, that's what we're trying to do. The photoanode too. That's kind of interesting. Photoanode. This is a voltmeter here. Some kind of resistor. And so the solar energy is hitting this. Not here. Sorry. Here. Here, we don't need a salt bridge. You don't need a salt bridge if it's all in one container. It can all be in one container because we don't have to worry about direct reaction. If there's no energy, there's no reaction. So we can turn this off immediately by blocking off the light. And so we don't have to worry about this reacting. So, you know, electrolytic cells can be 2 beaker or 1 beaker. In this case, it's 1 beaker. Voltaic and galvanic cells have to be two, you know, you need a cathode compartment and an anode compartment. These are diagrams showing potentials. You know, this is the mathematics. This is a solar spectrum in terms of intensity. The solar spectrum, the spectrum from the sun consists, you know, of a lot of visible light and some UV. We get UV from the sun and infrared. And so this is the solar spectrum here from the sun. This is what it looks like. It's kind of choppy like this because there's certain things that are taken out due to absorption by atoms, you know, and rotations, vibrations, other stuff like that. A lot of research is going into this, you know. Yeah. Okay, well, that's probably enough. I'm going to save this. I mean, if they're giving this paper for International Hydrogen Energy Review. If they're giving this paper away, I'm going to take a copy of that. But it's a little old, 2002. So I'll just save it on the desktop. Normally, they'll only give the abstract for free, like this paper. If we look at this paper, I don't know when this was published. See, the cost, if I want to buy the paper, it's going to cost me 30 bucks. Well, they don't, where's the year publication? So basically all they give me is the abstract. The abstract is a 1-paragraph synopsis of the paper. So here's a preview. They're teasing you with the paper here. So this just gives us the first 2 pages of the paper. This is 2007. But if I wanted the whole paper, $30. Oh, the book is 120. So the book probably has a whole bunch of papers about hydrogen as a fuel. Sorry. IEEE, those electrical engineers are into this. IEEE is for the electrical engineers. Obviously, electrical engineers have to be into this. So they got to design it here. Solar panels. Oh, this is a prototype. The prototype takes the water vapor and splits it into hydrogen and oxygen molecules. There's a rooftop unit. Wow, can you imagine all the roofs generating their own hydrogen? 250 liters of hydrogen gas per day. Belgian. What was this? 2019. Wow, that's pretty good. And so you just put in water. You put in water there and you get hydrogen and oxygen gas. That's pretty cool. 250 liters. 250 liters is really tricky. 250 liters, well, what's the pressure, right? And what's the pressure and what's the temperature? And then we'll have a better idea if we're getting any gas or not. And so this is probably under normal conditions. So maybe under room temperature and atmospheric pressure. If it's under normal conditions, then it's 25 liters per mole. And so this would be 10 moles of hydrogen gas. 10 moles of hydrogen gas is about 2 grams per mole. So that's about 40 grams of hydrogen gas per day. That's pretty cool. Yeah. So we'll see where that leads. All right, then, so that's a little bit about batteries, you know, voltaic and galvanic and electrolytic cells. Electrolytic cells are used to generate, you know, high energy reactive materials like hydrogen gas, sodium metal, chlorine gas. You know, those types of things are too unstable to exist, you know, on the surface of the earth here. So oxidation numbers, you know, we already went through those. Let's look at this one here, discharging and recharging.
When a lead storage battery discharges, lead at one electrode is converted into lead-2 sulfate. At the other electrode, lead dioxide is also converted into lead-2 sulfate.
So here, discharging, I like to go left to right. So electrons are flowing left to right here, and they're powering something here, you know. This is the normal battery. And we have the oxidizer. The oxidizer is weird. It's lead-4 oxide was the oxidizer, but.
The lead sulfate in each case adheres to the underlying electrode. When the current is reversed, electrons transfer from one lead sulfate electrode to the other, and the battery is thereby recharged. If the lead sulfate did not adhere to the electrodes, recharging would be much slower.
There are different ways we can make chlorine. One way we can make chlorine is by electrolysis. We can electrolyze molten sodium chloride. This is a chemical reaction. This is a redox reaction here. So they're using dichromate in acid. Dichromate in acid can oxidize chloride in sodium chloride to form chlorine gas. And so dichromate's a great oxidizer here. And they're generating the yellow-green chlorine gas over here. That's laboratory generation. We can also generate it using electrolysis, which there's a photo of that in an earlier chapter. It's like these chlorine generators. We had a photo in the book. I forgot what chapter it was. Sodium hypochlorite here, chlorine dioxide generator. Saltwater pools work that way. You know, saltwater pools, you put salt in the pool and then electrolyze the salt. When you electrolyze the salt, you make chlorine gas. And so saltwater pools have salt water, and then it's pumped through an electrolysis apparatus making chlorine. And so you can chlorinate the pool that way. Here are the rules for assigning oxidation numbers or oxidation states. Written below. Here's another redox reaction here. What's going on? The oxidation of aluminum with bromine. So aluminum metal and bromine. Bromine's a liquid, but it's a pretty volatile liquid. Look at how much bromine gas is being generated here. So it's very volatile. And you put the aluminum in here and it gets hot. If it gets hot, obviously you're going to vaporize more bromine. And then we're going to get a reaction. We're going to form aluminum bromide here. So it looks dirty. It has to be washed and cleaned and all that other stuff like we were doing the other day. Just take a look here. The reaction.
Aluminum foil is added to a beaker. Liquid bromine is poured in. They react.
Oh, sparks. There's some redox going on there. That's a pretty violent reaction there. All right, it's a break time now, so I'm going to pause the recording and we'll take a 15-minute break, start up after the break. All right, let's use some oil rig type analysis here. This is the reaction in car battery, you know, and so we're gonna take a look at what is the oxidizer here. And so it's kind of hard to, you know, maybe it's H+, maybe it's sulfate and H+, but it's kind of hard to see without first writing out the oxidation numbers. Well, the first thing we do is take a look. Elements are 0. And then oxygen goes first in a compound here. And the -2 times 2 is -4. That means lead is +4. This is just +1. That's charge here. Oxygen goes first in this species. -2 times 4 is -8. -8 plus 6 will give us -2. So this is +6. And going over here. Now, this is going to be lead 2 sulfate because we know sulfate's already -2. So this we know is got to be lead 2, not lead 4. Oxygen is -2, and that means sulfur is +2. 6. In fact, sulfate doesn't change, so it's still going to be 6. It's plus 6 over here in sulfate, and it's going to be plus 6 here in sulfate. And then hydrogen goes first here, plus 1, and then oxygen's at minus 2. And so let's see what did not change. What didn't change is oxygen. Oxygen's minus 2, minus 2, minus 2, minus 2. So oxygen doesn't change. Hydrogen doesn't change. Plus 1, plus 1. Sulfur doesn't change. The only thing that changed is lead. And so it's kind of weird. This lead here goes from 0 to plus 2. In order to go from 0 to plus 2, it had to lose electrons. And so this is called oxidation. Oxidation is loss. And so this lead is oxidized. Over here, this lead went from plus 4 to plus 2. To go from plus 4 to plus 2, we had to gain electrons. And so this is reduction. Reduction is gain. And so what we say is lead metals oxidized, lead ion here in PbO2 is reduced. Now, what that means is whatever is reduced is our oxidizing agent. It's taking electrons. And so this is our oxidizing agent. It's the lead ions here. Lead 4 is the oxidizer, and lead 0 is the reducer. This is a reducing agent here. So in a car battery, you know, your oxidizer is actually a solid oxidizer. It's lead. And the anode is, this would be the cathode. The cathode would be over here. And the cathode is, the job of the cathode is to feed the electrons to the oxidizer. Over here, the anode is being, it's a reactive anode and it's being oxidized to supply electrons to the car battery. So this is your lead storage battery or just car battery. Here, you know, elements in elemental form are 0. This is a redox reaction. This is 0. This is 0. This is plus 1, minus 2. This is going to be plus 2. This is going to be plus 1 and minus 2. So the oxygen, one oxygen, this oxygen didn't change. Actually, we have 2 of them here. 2 of the oxygens don't change, but 2 of the oxygens do change. We go from 0 to minus 2, so that's gaining electrons. So oxygen is reduced. That's reduction. And this is our oxidizing agent. Our oxidizing agent is reduced, gaining electrons. And this will be our reducing agent. The reducing agent is oxidized. Who's the reducing agent oxidized by? The reducing agent is oxidized by the oxidizing agent. So the oxidizing agent oxidizes the reducing agent. Therefore, the reducing agent becomes oxidized. And so those terms get mixed up all the time. So repetition helps for remembering. So now oxidizing agents and reducing agents. Oxidizing agents are electron poor, and reducing agents are electron rich, you know, ideally. This is the thermite reaction. Do you guys remember the thermite reaction? Thermite reaction takes rust and aluminum. And this is highly exothermic. And so it's so exothermic, it's going to produce molten iron. So it's iron liquid. Aluminum oxide is extremely hard to melt, and this stuff is stable. It's thermite. This is the thermite reaction in action. Here. The iron 3 in the rust is the oxidizer. Aluminum is a good reducer. This is another example of redox. This is their chlorine generator. Actually, using manganese 4 rather than permanganate. Manganese 4 oxide, chloride. Right, chlorine. Nitrate is a good oxidizer, especially in acid. In this case, there's no acid here, but there's water substitute. This is nitric acid again, nitrate and acid. The copper metal being oxidized here. And the copper metal is the reducing agent. The reducing agent gets oxidized in the process, going to copper 2, and the oxidizing agent gets reduced in the process, going to NO. Strengths of oxidizing agents and reducing agents. We just look at the chart. The strongest oxidizer is fluorine. Okay. This chart's very similar. The weakest oxidizer is lithium ion. The strongest reducer is lithium metal here. The weakest reducer is fluoride. There are weaker and stronger species, just not listed on the chart here. Fluorine's extremely reactive, so it doesn't exist naturally. So they're using electrolysis here. They're potassium fluoride, a molten mixture of potassium fluoride with hydrogen fluoride. So there's molten potassium fluoride, and they're going to strip electrons off fluoride using electrical power source here. So the pluses and minuses are. A solid iron with chlorine gas. You know, iron again is a good reducer, chlorine's a good oxidizer, so you're going to get a reaction here. Let's take a look at the reaction.
When heated iron comes in contact with gaseous chlorine, a reaction immediately takes place, forming a dark brown solid, iron 3 chloride. This oxidation-reduction reaction involves a transfer of electrons from atoms of iron metal to atoms of chlorine, a halogen.
Okay. When we predict redox reactions, we look for a driving force, you know. We could use the activity series if it's single replacement, or we could use the chart that was shown earlier for more complex reactions. Okay. Same kind of thing. We want to go from stronger oxidizer to weaker oxidizer. So we want to go downhill, basically. Downhill on the oxidizer end, and then that would be equivalent to going uphill on the reducer, because the reducer end's inverted, you know, side down. So we could predict this here, you know, this is our oxidizer, here's our reducer. Going backwards, this is our oxidizer, this is our reducer. So we compare the two oxidizers, cobalt versus silver, what's a better oxidizer? Or we compare the two reducers, you know, what's a stronger reducer, silver or cobalt metal? It depends on which chart you use now. This one is for the redox chart. But if you look at the activity series, the activity series is an upside down redox chart. Lithium's at the top. And so lithium is the strongest reducer. So this is just one half of the redox chart. It's just looking at the reducer. And if you use the activity series, what you want to do is you want to go from a stronger reducer to a weaker reducer. So in the case of the activity series, you want to go from high to low. In the case of a redox chart, lithium's at the bottom, so we want to go from the redox chart, we want to go from low to high. That would be favorable. So in the redox chart, we go from stronger reducer to weaker reducer, low to high. For oxidizers, we go from high to low. And it's just relative, depending, you know, it's because it's flipped, it's the conjugate chart. In which direction will this be favored? So we compare tin 2 versus sodium ions. Well, tin 2 is a stronger oxidizer. And then we look at the reducers, sodium metal versus tin. Sodium metal is much more reactive. So this is going to be forward direction for it. Okay, next. A metallic copper does not react with a strong acid to release hydrogen because copper and hydrogen ion are weaker reducing and oxidizing agents than hydrogen gas and copper ion respectively. Here. It doesn't react with mineral acids, you know, so you put the pennies in here, it's not going to eat up. If you have HCl, it's not going to eat it up. But if you have nitric acid, it'll eat it up. Let's look at that reaction here. We'll look at copper and HCl. I have to speed this one up. Only 1:22, so this will.
Take some copper oxide in the test tube.
No, this is copper oxide. I don't want copper oxide, sorry. Copper oxide is going to dissolve in HCl. This is the black coating. Copper oxide, copper 2 oxide is the black coating. Copper 1 oxide is kind of a red-orange coating.
Add dilute hydrochloric acid to it, drop by drop, and shake.
Acid will eat up that coating, the oxidation coating there, and then your pennies are going to come out clean, but you're going to lose some copper.
The solution has turned green.
That's from copper ions going into solution. It's fairly
The
concentrated.
copper, which was in insoluble form in copper oxide, has reacted with.
Okay, this is not the video I wanted. Your pennies are going to come out clean because they could have oxidation, this black layer on them, but it's not going to dissolve the underlying copper. And so, there's copper here. This is HCl, so there's tin, iron, magnesium.
A lot of stuff.
Yeah, the magnesium, the zinc, and the calcium are very reactive. The iron is a bit slower, and the tin's a bit slower, and the copper is unreactive here in terms of that. Look at the calcium. Wow.
You're welcome. All right.
Okay, let's take a look at the redox chart here. We're going to look at their redox chart. Where did I put their redox chart? It's here. So we use the same kind of pattern here, you know, to figure out the driving force. So let's take a look at the redox chart here. Now something like HCl, the oxidizer is H+. And so if we want to go downhill on the oxidizer end, it's kind of uphill on the other end, H+ will oxidize all these metals. And so H+ will oxidize lead. When H+ oxidizes lead, we form lead 2+. So here we're going from stronger oxidizer, H plus, to weaker oxidizer, lead. And when H plus oxidizes lead, it's reduced to hydrogen gas. And so here we're going from stronger reducer, lead, to weaker reducer, hydrogen. And so we go downhill like that. We don't want to go uphill in the sense, you know, uphill is, this is very, not very scientific because the chart could be flipped other ways. So for example, H plus and copper metal. So if we try to oxidize copper metal to form copper 2 plus, here we're going from a weaker oxidizer to a stronger oxidizer. And so in this case, going in this direction is not favorable here. It is weaker to stronger. And the same thing here. We're going to go from hydrogen we compare hydrogen and copper. Well, hydrogen is stronger than copper, so we're getting rid of the copper and producing hydrogen, so that's unfavorable too. And so what that means is H plus can oxidize lead, tin, nickel, cobalt, cadmium, iron. It was sluggish with the tin and the iron. Cadmium, iron, zinc, aluminum, magnesium, sodium, calcium, strontium, barium, rubidium, lithium, potassium, lithium. So we're going to oxidize all these. However, H plus can't oxidize copper metal. It can't oxidize silver. If you try to dissolve silver in HCl, it's not going to work. Here. Because reacting silver is going to form silver ion. And then you compare H plus versus silver. We're going from a weaker oxidizer to a stronger oxidizer. Weaker oxidizer to a stronger oxidizer is not favored. Here. So we could use the chart in this pattern here to figure out the chemical properties. Here. Our redox chart. And so going up this way is not favorable. Going down this way is favorable. Let's see what else we got. Okay, some batteries, different kinds of batteries, alkaline batteries, dry cell, etc. Here's a, looks like an alkaline battery here. And so the name alkaline, the way I can tell this is an alkaline battery is because it has alkali in there. Alkali is, you know, alkali metals is because you can mine like potassium hydroxide. There are potassium hydroxide deposits and that kind of stuff, alkali deposits. Potassium, it's got alkali in there, which is a base, hydroxide. And so I could tell. Now, what is the oxidizer in this? The oxidizer is actually MnO2. This isn't the best diagram for this. The graphite's black. And so the oxidizer, what's taking the electrons in this battery is manganese 4 oxide. Manganese 4 oxide is a pretty decent oxidizer, but the problem is it's a solid. And so how's it going to come into contact with the electrode? We need it to come into contact with the cathode. And so which one is cathode here? Excuse me. The cathode is just this metal plate, steel probably, or stainless steel or something. And so that's it. It's not going to come into contact with it. And so that's why it's surrounded by graphite. There's a whole bunch of graphite. Graphite is electrical conductor. And so graphite will ensure, even if the manganese is stuck in on one side, let's put a crystal. Let's see, there's a crystal of manganese oxide here. It can come into electrical contact because it's surrounded by graphite here, all the way to the cathode. The cathode is this metal. This is going to be an inert cathode in this case, just a steel can. Here. Okay, what's pulling on the electrons from the cathode? What's pulling on the electrons from the cathode is the MnO2. But where are those electrons coming from? Those electrons are coming from the anode. And so the anode here is a brass current collector. Where's the anode? Oh, anode's zinc. So, here. And then we have some KOH alkaline in there. There's other stuff, so it's a bit more complicated than what I made it out to be, but I don't think we need to get into all the details for this. Except for one. Let me show you one detail. One thing that happens is as the reaction proceeds, the concentrations go down. As the concentrations go down, so does the voltage. You know, the voltage is going to depend on, you know, the concentration. So if you have highly concentrated oxidizer versus a very dilute oxidizer, the highly concentrated oxidizer is going to have a greater pull for electrons. And so it's going to have a higher voltage. Well, this brings up the strategy in these batteries. A lot of these batteries are all solids or pure liquids. If you have pure solids and pure liquids, then the concentration doesn't change. The concentration is fixed, so it gives you a stable voltage. You know, normally, if it's just a regular concentration, the voltage just starts to drop as the reaction takes place. You know? And for a lot of things like an LED, you know, you need 3 volts. If it goes below 3 volts, it's going to stop working. And even though the battery still has life left in it, it just doesn't have enough voltage. Sometimes we can't get a high enough voltage. So in a car battery, they have 6 2-volt batteries attached in series, they call it. So 6 2-volt batteries attached in series gives you 12 volts. So we can get 12 volts from a car battery. This is the car battery here. And we can compare redox and acid base. We kind of already did that earlier. Writing redox equations, we did that. This is skeleton redox. This one we don't have to. This is already in the chart. Nitrate goes to NO is in the chart. It's nitrate plus 4H plus 3 electrons yields NO plus 2 waters. That one we can just copy down off the chart. This one we can copy off the chart. Iodide goes to iodine. This one is not on the chart. Sulfate goes to sulfur. And so sulfate goes to sulfur, we'll have to figure out using this method, the skeleton redox method. We can copy the other one off the chart. 2 iodides goes to iodine plus 2 electrons. Oops, that's something. It's talking about sulfur, chromate, etc. sulfur dioxide. This is potassium permanganate. You know, we tried to make this stuff, the purple liquid, which is aqueous potassium permanganate. Potassium permanganate will oxidize chloride to form chlorine gas. Okay, let's take a look at some of the concept problems. I'll be right back. I just need to grab a cup of coffee. I'll be right back. All right, back here. I forgot to pause it, but it'll be a gap. So let's take a look at some of these problems here. Electrolytic cell, electrolyte, voltaic cell, electrolysis, galvanic cell, electrode. What are we supposed to do here? Brief relationship. Electrolytes are just salt solutions. Oxidation, reduction, oxidation, half reaction, reduction, half reaction. Oxidation, reduction, oxidation number, oxidizing agent, reducing agent, oxidizer, reducer, strong oxidizing agent, weak oxidizing agent. Okay, let's skip those. Using any example of a redox reaction, explain why such reactions are described as electron transfer. Yeah, electrons are transferred because one, loses, the other gains. Yes. Classify each as oxidation or reduction. So oxidation is loss. So this is losing electrons here as product. So oxidation. Reduction is gain. This is gaining electrons. So this is reduction. This is losing. This is losing. Oh, oil. Right. Classify each of the following. Oops. That's so dissolving ozone in water. So ozone and water. This is a half reaction because there are electrons there. A full reaction would never have electrons like this. And so this is ozone and water is the oxidizing agent. And it's going to form O2 hydroxide. So this is a reduction half reaction. Dissolving gold. This is an oxidation half reaction here. This is not the complete reaction, by the way. Gold doesn't magically dissolve by adding sodium chloride to it. If you could add sodium chloride to gold, it'll be different. But this is a half reaction, so you need something to take those electrons away. It's oxidation. One side of the automobile battery. And so the PbO2 is the oxidizing side. So this is the oxidizer, so reduction. Combine the following to produce a balance. So this one produces 3, this one consumes 2. So I need to multiply the top one by 2, the bottom one by 3. So we've been doing this type of stuff earlier. The electron should balance. The electron should cancel. This is wrong here because in the net reaction, we should have no electrons. In net redox reaction, there cannot be free electrons. Free electrons just means there are electrons. Here, can't have that. And so this is supposed to be plus 6 chlorides here. The electrons cancel. 6 electrons consumed, 6 electrons produced. Alkaline batteries are manufactured in a variety of sizes. So, they try to keep as many solids in there as possible to keep the voltages stable. Okay, this is the oxidizer here. This is peroxide. An electron. There's a reducer here, cadmium and hydroxide. Which equation is for the oxidation? Oxidation is loss. So the second equation. Write the overall equation. Oh, here's the overall. These cells use zinc, though. This would be called a NiCad battery. NiCad batteries aren't these kind of batteries. None of these are NiCad batteries here. NiCad batteries, the problem with NiCad is cadmium is much more toxic than zinc. And so NiCad batteries aren't, like the common ones like here. Not only that, the oxidizer, they use a cheaper oxidizer. They don't use this. You know, the reason they use these is because it's rechargeable, but none of these batteries are rechargeable here. Once these batteries are done, you have to throw them out. And these batteries use a much cheaper oxidizer, MnO2, so that, and a much cheaper and less toxic reducer, zinc. But the drawback is that reaction is not very easy to reverse. List as many things in your home as you can that are operated by voltaic cells. Skip that. Can a galvanic cell operate an electrolytic cell? Yes. You know, you can throw a galvanic cell to force the electrons to go backwards. That is, you can put a battery there instead of using an electrical power source to force the electrons to go backwards. The next 4 questions give the oxidation number of the elements whose symbol is underlined. +3, -2, +6, +6. Or actually, no, this one's +6. This is sulfite. So that's -2 times 3 is -6. This is going to be +4. -6 + 4 gives us -2. This is going to be sulfate is +6. Nitrogen here, got oxygen goes first. -2 times 3 is -6. This has got to be +6. Divided by 2 is +3 each. +3. This is -2 times 3 is -6. This is going to be +5. This is -8. This is going to be +6. This is -8. It's going to be actually, what was I here? -8, it's going to be +6, and this is -8. Well, actually, sodium goes first, so do this one. And then oxygen, so that's +3, -8 is -5, so this is going to be +5. Identify the element experiencing oxidation or reduction. State oxidized or reduced. Okay, so here they're giving an example. Chlorine is oxidized from -1 to 0. So we start off with chlorine in the -1 or chloride. And go on to elemental chlorine. Oxidize is losing electrons. Here, bromine's gaining electrons, so it's reduced. Bromine is reduced from 0 to -1. Bromine reduced from 0 to -1 here. Okay, something's being oxidized here. It looks like lead. Lead's being oxidized from Pb2+ to Pb4+. So lead ions are being reduced from +2, or not reduced, oxidized. Lead ions are being oxidized from +2 to +4. Let me go over here. Something is being reduced here. So H doesn't change. It's the iodine. You know, if we look at peridate, it's -2 times 4 is -8. -8 plus 7 gives us -1. So iodine is going from +7 to -1. Here, oxygen is being reduced. You know, hydrogen doesn't change. Oxygen is going from 0 to -2. Okay. Nitrogen is being oxidized from +4 to +6, or no, +5, sorry, +4 to +5, losing 1 electron. Chromium-3 is being oxidized from +3 to +6, and dichromate is +6. Okay. Let me do this. 27, identify the oxidizing and reducing agents here. So bromine is going to be the oxidizer, iodide is the reducer. When aqueous bromine orange solution is added, 2 different solvents. Separate the products. What is the oxidizing agent in the equation for the lead storage battery? The oxidizing agent is PbO2. We already saw that earlier. PbO2. Which is the stronger reducer, zinc or iron 2? We would think zinc would be easier to lose electrons than iron 2. Iron 2 has already lost 2 electrons. So lose a third one, but probably zinc is more powerful reducer. Let's see what they base their decision on. From table 19.2. Yeah, if we look at the table, then we can see, you know, just based on the table. Actually, the table is not really there. The redox chart. So if this is looking at the redox chart, then it's simple. Arrange the following oxidizers in order of increasing strength. That is the weakest oxidizer first. Well, we could use the chart for this if we want, you know. And so it would go bromine. Looking at the chart, it would go bromine, copper 2, iron 2, and sodium. It's the strongest, sorry. I went from strongest to weakest. I guess they wanted the weakest to strongest. So bromine, copper 2, iron 2, and then sodium. Write the redox equation. So these are a little simpler than the ones I may have given you because fewer possible choices here. So we know bromine's an oxidizer, iodide's a reducer. And then we could just copy the charts off the reactions off the chart. Bromine plus 2 electrons goes to 2 bromides. And then 2 iodides goes to iodine. Oops. Plus 2 electrons. It's here. And then add these. 2 electrons are being consumed, 2 electrons are being produced, so we could just add those straight. We don't have to multiply by any coefficient for those. Oh, then they want the driving force. So the driving force is we got to compare the 2 oxidizers, bromine versus iodine. Bromine's stronger. Bromine versus iodine. Bromine's stronger, so we got reaction. H plus bromide. So H plus is an oxidizer, bromide is a reducer. And so in this case, we would just set it up here, just kind of off the chart. And so off the chart, 2H plus 2 electrons goes to H2 gas. And bromide. Actually, let me do that over here. Bromide, 2 bromides goes to bromine plus 2 electrons. And then we can add those up. Then we can look for driving force. So this is redox we're looking at by the chart method. Okay. All right, let's see. It's getting close to break time. Let me actually let me finish this one. So 2 electrons here, 2 electrons here. So the net reaction is 2H plus 2 bromides yields H2 gas plus bromine gas. And then we compare, this is the oxidizer in the forward, this is the oxidizer in the reverse, this is the reducer in the forward, this is the reducer in the reverse. And so comparing the oxidizers, which one's stronger, H plus or bromine? Okay, here we can go back to the book and take a look. See if I can get that. Well, anyway, I am going to just base it off, not the chart, but what's easier to burn, hydrogen or bromide? Well, hydrogen is easier to burn. And so in this case, we're going from weaker to stronger. If we're going from weaker to stronger, we expect no reaction in this particular case. So I was going to flip back, but I don't think so. All right. Well, anyway, it's about time for a break. So let's take a break right now, and then I'll be back in about 15. Okay, back now. Let's take a look. Here. All of this half reactions. Well, they're asking us to take a look at these half reactions here. I don't know what number I was just on. Okay, we'll just go to this one. Cadmium is an oxidizer, it's taking electrons. Lead is an oxidizer, taking electrons, and chlorine is an oxidizer, taking electrons. And they probably just want us to consult the chart, so we just figure out which one's the strongest. Chlorine, the strongest. Then look at the others. Then the reducing agents would be the opposite trend. Oh, here, bromine and iodide. And so we looked at that. Forward reaction, yeah, bromine's a stronger oxidizer than iodine. We could tell by size too. Bromine's smaller than iodine here. Let's take a look at this one. What would you predict for number 37? Take a look at that and tell me what you guys get. So this one's kind of a weird one, number 37, because number 37 is hydrobromic acid. You know, hydrobromic acid is strong acid, strong electrolyte. So if we had HBr, HBr in solution would consist of H plus aqueous and Br, bromide aqueous, Br minus. And so this one I expect no reaction to occur because hydrobromic acid forms a stable mixture here. So, but we could predict the redox reaction. You know, this is our oxidizer, this is our reducer. And so our oxidizer is going to be H plus. So we copy it off the chart. 2H plus 2 electrons yields H2 gas. And then bromides are going to be our reducer. So we'll take 2 bromides. It's going to go to bromine plus 2 electrons. Now the easiest, this is what, when we're doing redox, the easiest spot to determine the oxidizers and reducers in reverse are from the half reactions. And so if this is my oxidizer, this reducer, this is my conjugate oxidizer. And so the net reaction here is 2H plus 2 bromides. I'm going to cancel out the electrons here. This is going to yield H2 gas plus bromine. And so we're comparing H plus versus bromine. Which one's a stronger oxidizer? And looking at the chart, this H plus is a weaker oxidizer, bromine's a stronger. And the same thing goes with the reducers. Bromide is a weaker reducer. Hydrogen is a stronger reducer. And so the driving force is the reverse here. If the driving force were forward, then hydrobromic acid would not be stable. It would react. And so this is the most probable redox reaction. There's one other species here. The one other species is water, you know, because we have water present. And what they're doing is they're eliminating water as a potential reactant here by not listing it. Also, they don't list any other species that might be present as well. So they're keeping these a little simpler than if it were open, you know, to. So reverse reaction is favored here. Okay, what about this one here? NO, I know from the chart, NO in water is a very weak reducer. I've seen the chart quite a few times. And actually, this is the conjugate reducer of nitric acid. And then we have iron 2. Iron 2 is amphoteric. And so we don't have too many choices here. NO in water, this is a reducing agent. Iron 2, this is an oxidizing agent or reducing agent. In this case, we can't have 2 reducing agents react, so we've got to pick one. And this is the better reducing agent. Or actually, I don't know if NO and H2O is a better reducing agent than iron 2. We have to look that up on the chart. And so let me go to the chart and we'll take a look at that chart. And so we're comparing the 2 reducing agents, NO versus iron 2. chart. It's weird. All right, let's get a handout. So in this particular one, we're comparing NO and H2O, is here, NO and H2O to iron 2. So which one's a better reducer? It looks like iron 2 is a stronger reducer than NO and H2O. And so the reaction mixture that they gave us consisted of this. So just keep that in mind. Iron 2 is a better reducer than NO and H2O. So going back to this, I had it labeled out, but I need to relabel this because I selected my reducer too prematurely. And so I have NO and H2O, that's a reducer. And then I have iron 2, which is also a reducer. Which of these two is stronger? Iron 2 is stronger. This is not an oxidizer, but iron 2 is also an oxidizer. This is water. And so what's the stronger oxidizer? Water, actually. I should have done this. NO and H2O is a reducer. Water alone is a reducer. And iron 2 is a reducer. And so out of those three, iron 2 is. As far as oxidizers go, H2O is an oxidizer and iron 2 is an oxidizer. So it turns out the oxidizer is going to be iron 2. And so the strongest oxidizer is iron 2. And so iron 2 can gain 2 electrons to form iron metal. This is the strongest oxidizer present. The strongest reducer present is iron 2. Iron 2 can go to iron 3 plus an electron. How we figured that out is by looking at the chart. You know, we had various choices and it turned out iron 2 is both the strongest oxidizer and the strongest reducer present. And so the second reaction will have to, a half reaction will have to multiply by 2. And so the net reactions, iron 2 plus 2 iron 2 plus. Okay, so we have 3 iron 2 pluses. Out of the 3, 1 is a oxidizer and 2 are reducers. This is going to produce iron metal plus iron 3 plus, 2 iron 3 plus. And the electrons cancel. We got 2 electrons canceling out 2 electrons. So this iron 2 is acting as the oxidizer. These 2 iron 2s are acting as a reducer. This is a reducer. This is oxidizer. So now we compare iron 2 versus iron 3. Which is a stronger oxidizer? Well, iron 3 is, I don't need to look at the chart because it's plus 3. This is weaker. This is weaker. This is stronger. So there's no driving force for this here. But this is the most likely reaction. So I just picked the most likely. Your book likes to pick all the variations, even the less likely, but the less likely is going to have an even weaker driving force, and this has no driving force. So it's not even it's not even worth looking at right now. Okay, they did it different though. They didn't pick the strongest reducer here. So this is not the most likely reaction to occur. You know, the most likely reaction occurs between the strongest oxidizer and the strongest reducer. And so I wouldn't have selected this reaction as the most likely reaction. Well, anyway, this reaction doesn't even have a driving force either. In fact, the driving force for this reaction that they selected is going to be even worse than this. And this one's not good in the forward direction. And so they did it wrong there in terms of being able to figure out some general reaction. Explain how a strong acid is similar to a strong reducing agent and strong base compares with strong oxidizing agent. Strong acids release protons readily, a strong reducer releases electrons readily. So this is the same answer they had earlier in the acids chapter. So we saw that already. Now these are skeleton redox reactions. And so for skeleton redox reactions, we split it up into skeleton half reactions. And so here we have thiosulfate and chlorine going to sulfate and chloride. And when we split these up here, thiosulfate goes to sulfate. So we can do that, figure it out. And so one half of this is thiosulfate goes to sulfate. I don't know that's oxidizing or reducing or whatever. And the other half is chlorine goes to chloride. Well, chlorine goes to chloride is easy. We copy that off the chart. If we copy that off the chart, then we have chlorine plus 2 electrons goes to 2 chlorides. And so we're done. This one's not on the chart. Not on chart, and therefore we have to use the skeleton redox method to solve it. And so over here we have 2 sulfurs, over here we have 1 sulfur. And so we multiply by 2. So we're going to put 2 sulfates there. Over here we have 3, that's 3 oxygens. Over here we have 4 oxygens. And so we add 1 water to this side here. And then over here we have 2 hydrogens from the water and no hydrogens up there. So there's 2 hydrogens. And over here we have no hydrogens. And so we add 2H plus. And then we look at the charge. Thiosulfate's -2, water's 0. So we have -2 on the left. On the right, we have 2 times -2 is -4 plus 2 is minus, is that -2? -4 plus 2 is -2. That's odd. And so here, there is no change here in the charge. And so that's odd because normally we have to add electrons, on one side to have an oxidation half reaction or a reduction half reaction, but in this case it's pretty strange. So let's take a look at the oxidation states here and see what's happening with the oxidation states. So oxygen's -2. And that's going to oxygen -2. So nothing's happening to oxygen. So what's happening to sulfur? So if oxygen is -2, that's -2 times 3 is -6. -6 plus 4 will give us -2. Plus 4 divided by 2 is +2 here. And then over here, it's -2 times 4 is -8. -8 plus 6. So sulfur is going from +2 to +6. So it's losing electrons. It's losing electrons. And so I should have electrons over here on the right. And so somehow I screwed this up. I don't know how I screwed that up. Oh. Oh, I see how I screwed it up. I screwed it up as here. I miscounted. Here I have 3 oxygens. Here I have 4 oxygens times 2. So 4 times 2 is 8 oxygens. And so that's 8 oxygens. So I don't add a water here. That's going to change these. Sorry. Let me fix that. And so if I have 3 oxygens here and 8 oxygens here, I need actually not 1 water. I need 5 waters. 5 H2Os. That'll give me 8 oxygens on the left. That's going to give me 10 hydrogens on the left and no hydrogens on the right. This I could have caught if I double checked the balance as well. And so this is going to be plus 10H plus over here. Now let's look at the charge. -2 from thiosulfate plus 0 is going to be -2. And then over here, -4 plus 10 is going to give us plus 6. So to make these balance, I'm going to have to add 4 electrons, 4 negative charges. Oh no, 8 electrons, sorry, 8 electrons. If I add 8 electrons, they'll take, 6 will take it down to 0, and then an extra 2 will take it to -2. And so that's what we have here. I could have caught this later, the mistake. I just noticed the mistake here because there are no electrons to add. You could have caught it, the mistake here, even if I added electrons, I still might have made a mistake. So we'll go S2O3 2 minus plus 5H2O liquids yields sulfate. This is aqueous, so I'll just omit that, plus 10H plus 8 electrons. The way I can check it here is just to make sure atoms balance and charges balance. And so 2 sulfurs, over here I'll have only 1 sulfur, so I already made another mistake. It should have been 2 sulfates here. Gives us 2 sulfurs, 2 sulfurs. 3 oxygens plus 5 oxygens, 8 oxygens. So 2 times 4 is 8 oxygens. 10 hydrogens, 10 hydrogens. And then make sure the charge balance, minus 2 on the left, minus 4, plus 10 is plus 6 minus 8 is minus 2. So minus 2 and minus 2, this checks out. And so here we have 8 electrons. Here we have 2 electrons. So I need to multiply this one by 4. And so that'll make 8 electrons here on the left and 8 electrons here on the right. We'll combine these two, add them up, and that will give us the net redox. And so that's going to be shown here. Let's take a look. So this is the equation we just generated. This is the equation from the book, multiplied by 4, add them up, and that gives us our net redox. In skeleton redox, there's always a driving force. And so this is why they aren't listing the driving force here, because in order to get products, we have to have a driving force. Go to the next one. Tin goes to this one. What would that be? Stannous acid. And then a nitrate goes to nitrogen dioxide. Both of these aren't on the chart, so we'll have to do both of them by this method. Here we have dichromate, or not dichromate, excuse me, that's not even chromium, that's carbon. This is oxalate. Oxalate goes to CO2, so oxalate is completely oxidized to CO2 via permanganate here. Oxalate going to CO2 is not on the chart. We'll have to figure that one out. But permanganate goes to manganese 2 is on the chart. You know, that one we could just copy out right off the chart. You know, here, permanganate plus 8H plus 5 electrons yields manganese 2 plus 4 waters. Okay, oxalate's not on there. Dichromate goes to chromium 3 oxides, not on the chart. I have to figure that one out. And then ammonium goes to nitrogen. We have dichromate on the chart. Dichromate on the chart goes to chromium 3. And so dichromate goes to chromium 3. We could just copy that, but this one's not going to chromium 3 ion like this. This one's going to chromium 3 oxide. Here. This is different. And so we do it the same way. Here we have arsenic 3 oxide going to arsenate. That's not on the chart, so we'll have to figure that one out. But nitrate going to nitric oxide is on the chart. This one we'll just copy off the chart. Nitrate going to nitric oxide. This nitrate plus 4H plus 3 electrons goes to nitric oxide gas plus water, 2 waters. That's on the chart. True or false? Oxidation reduction occur at the electrodes in a voltaic cell. That's true. The sum of the oxidation numbers in a molecular compound is 0, but in an ionic compound, that sum may or may not be 0. In ions, it may or may not be 0. Moleculars are supposed to be neutral. Ionic compounds are supposed to be neutral. So both of these should go to 0. But in ions, it need not be 0. So this is false. The oxidation number of oxygen is the same in all the following. This is 2 minus, this is 2 minus, this is 2 minus, this is 2 minus. That's true. The oxidation number of alkali metals is always +1, not -1. That's false. A substance that gains electrons is oxidized. No, oxidation is loss. A strong reducing agent has a strong attraction for electrons. No. Strong oxidizer has a strong attraction for electron. The favorite side of a redox equilibrium equation is the side with the weaker. Yeah, that's true. Just one, yeah. One of the properties of acids listed in chapter 17 is the ability to react with certain metals to release hydrogen. Why is this property limited to certain metals? Yeah, it's just the metals that we call active metals. And so when we look at the redox chart, the active metals here, this is mineral acid here, H+. And so mineral acids will oxidize all the active metals. So here's our mineral acid. So it'll oxidize any metal, lead, tin, iron, zinc, aluminum, magnesium, etc. These are called the active metals here. However, the noble metals aren't. And so copper is not, silver is not, gold, platinum, gold and platinum are up here. But they aren't listed on this chart here. Aluminum, yeah, aluminum is an active metal, reacts with acids. This property of an acid is more correctly described as a property of an acid acting as an oxidizing agent, yes. H+ ion only reacts with metals whose ions are weaker oxidizing agents. So we need a driving force is what they're saying. Questions based on 19.8 identify reactants that engage in a redox reaction and their oxidized and reduced products. You were to write the redox equation, nowhere among the reactants or products do you find a water molecule or a hydrogen ion, yet when writing the equation you added these species. Why is this permissible? Because we always balance. When we balance, you know, when we balance, we add hydrogens and water. You know, we balance out the oxygens by adding water. So we don't care if there's water. Oxygen and hydrogen, we don't really care if it's there or not because we will balance it nonetheless by adding water or by adding H+. So that's the reason why. There's a fundamental difference between the electrolytic cell and the voltaic cell. Yeah. One uses electricity, the other produces electricity. It is sometimes said that in a redox reaction, the oxidizing agent is reduced and the reducing agent is oxidized. Is this statement always correct? Yes, this is always correct. The oxidizing agent, if there's a driving force, the oxidizing agent is reduced and the reducing agent's oxidized. So it's always correct if there's a driving force. If there's no driving force, then it's incorrect. Okay, what are they saying here? Sometimes correct. In a simple 4 monatomic ion redox, the statement is correct. The element oxidized or reduced can always be identified by the change. The oxidizing agent or reducing agent, however, is a species that contains the element being oxidized or reduced, and it may be an element of a monatomic or polyatomic. I don't understand this answer here. I don't agree with this answer. As an example of an electrolytic cell, the text states, so let's see. Okay. This is generating chlorine by electrolysis and sodium metal by electrolysis. This is molten sodium chloride. This is a commercial reactor. And so they generate chlorine at the anode, or the cathode actually, is going to generate the, well, it depends. Anode and cathode get mixed up when you're dealing with electrolytic cells. So it depends on how you picture it, you know. At the cathode, oxidation always occurs at the cathode. And so this is technically, this is the cathode here. Just 1 minute. No. Just 1 second. But sorry about that. We're back here. Okay, number 60. Oh, jeez. Okay, here's number 60's answers there. This is electroplating. The electroplating is another technique here where we can deposit the copper. You deposit very slowly on the electrode. You can plate copper metal onto the electrode itself. So the electrode, you just got to make it a conductive material, and then you can plate metals on it. So you could electroplate copper, you could electroplate gold just by having a small concentration of gold or copper in here, and that's going to plate the metal out onto the electrode itself. Okay. And so this is electroplating. It's just using electrolysis to plate metals. That's about the extent you need to know. Marine equipment made of iron or copper alloys and through which seawater passes sometimes has inexpensive and replaceable zinc plugs sticking into. The zinc is, you know, whatever is going to be oxidized is the species easiest to oxidize. So if you put copper and zinc together, then an oxidizer is going to come along and pick the easiest one. Well, the easiest one is going to be zinc. So if you have copper, you want to protect the copper, then you attach a piece of zinc to it. And if an oxidizer comes sniffing around, the oxidizer is going to attack the zinc or it attacks you. So let's call it sacrificial. Call that a sacrificial anode. That's what it is. Just 1 second. I have to get some air in here. All right. And so zinc is used to prevent the copper or iron. So if you have some iron and zinc is easier to oxidize, you know, it's a stronger reducing agent. So if you attach the zinc to the iron and the oxidizer comes along, it's going to attack the zinc. This is called galvanized iron. Galvanized iron is you take an iron nail or a piece of iron and then coat it with zinc, molten zinc, and the molten zinc will solidify, and so it's zinc coated iron. Zinc coated iron, if an oxidizer comes along, then the oxidizer has a choice. It can oxidize the zinc or it can oxidize the iron. Well, it's going to pick the zinc. It's easier to oxidize. So zinc is a stronger reducing agent than iron or copper, and it's cheap. Have you ever put a piece of metal into your mouth, perhaps a paper clip or the end of a metal pencil, touched it to a metal filling in your teeth and tasted electricity produced? Whether you have done this or not, it does happen. Can you explain this phenomenon? Yeah, this is, you're just making a little battery in your mouth, and the electrolyte is your saliva. And so the moisture on your tongue becomes electrolyte. The electrolyte is the salt bridge for the passage of the electric current from one metal to the other. And it also is the wire. There's a salt bridge and the wire. And so you can taste that. So one of the metals is oxidized and the electrons travel. This actually, ions can conduct electricity too. All right, that's chapter 19 here done. So what we're gonna do is to finish the, we didn't cover nuclear chem, but nuclear chem's Covered it in general chemistry, Chem 1B. Organic chemistry, a little bit's covered in Chem 1A. Biochemistry is covered in neither class, but these 3 chapters we aren't going to cover here. But these are interesting, so if you're interested in it, these are good introductions to that. Sorry, I had to answer a question. A lot of these concepts that we learned here can be applied, to biochemistry. Biochemistry follows the same rules as regular chemistry. The same thing with organic chemistry. Organic chemistry follows the same rules. The rules are going to be a little bit more detailed, a little bit more involved for those particular systems. Nuclear chem follows a different set of rules. And so here, DNA, we got this nice helical structure of DNA from hydrogen bonding for that, etc. So this is a good introduction to biochemistry, if you're interested. Or if you're taking biochemistry, this is good for preparation. Same thing with organic chemistry, This is beta pleated sheets, this is alpha helix. All hydrogen bonding type interactions. We have quaternary structures, the protein folding. Protein folding is very important. Sometimes there's misfolds. Misfolds can cause things like Alzheimer's and other stuff. So another talk I went to at UCLA, which was last year, was a talk by a physicist about protein folding. It was a pretty interesting talk. And protein folding and aging, that's what it was about. Enzymes are biological catalysts. And so enzymes, the way they lower the, they have hydrogen bonding and other types of interactions with molecules. And so what the enzyme does is pulling apart. It's pulling on this molecule, making the bond easier to break. This bond is this is the bond they want to target. So the enzyme's kind of tugging and pulling on this molecule and weakening this bond. This is like what happened in my glass test tube. My glass test tube, I kept punching it. Actually, not me, but many previous people did, because it didn't take much to punch a hole right through it. Well, the same thing, this is stretching, it's pulling and stretching on this bond. And it significantly weakens this bond, making it a lot easier to break. And once that bond's broken, then the electronic environment changes there, and then it releases these molecules. So this is 2 sugar molecules here that are bonded together, and this one helps break it. Here. And so that's the operation of enzyme. It just provides an alternate mechanism. Now, if you didn't have the enzyme, there's nothing pulling on that bond. And so you have to break the full strength bond versus a weakened bond, weakened bond stretched out, like in the glass, a weakened bond there. And this is more a cartoon style drawing of enzyme substrates. Carbohydrates are sugars, like glucose, sucrose, fructose. These are all fuels, energy molecules here. Carbohydrates, CHO. Glucose is an example of monosaccharide. Sucrose is an example of a disaccharide. These are sugars, high energy fuels. This is glucose. This is the chair form of glucose. This is a 6-membered ring. These are tetrahedral, all tetrahedral. It's not flat like this, and it's not a straight line like this. These are all, glucose, ways of representing glucose. Here's a ball and stick. Although this ball and stick is hard to see, but you can see it's tetrahedral. Here, bent. There's alcohol groups here. This is what we call an ether type bond, COH. I mean COC bond here. Now it depends on which end this is pointed up, you know, and how it's bonded together. We have equatorial and axial when we're looking at tetrahedral, you know. Then you get much more into the structure of things here, the three-dimensional structure, these types of things. Sucrose has it bonded in this way here, you know, one glucose and one fructose. Here's a glucose, fructose. This is disaccharide, two sugar molecules bonded together. This is table sugar, which is sucrose. Lactose is another sugar. Lactose consists of, looks like two glucose, or no, galactose and glucose. You learn about these sugars. Amylose, starch. Glycogen. Fats, lipids, fats. This is a fat here. Yeah, saturated and unsaturated fats, etc. So it's pretty much the same stuff that you have. All right, so we have about an hour left. So the remaining hour, you guys can work on the labs. Now the labs, officially the labs are due tomorrow. I mean, we did finish that one lab this week, so you know, officially it would be due next week. But so I made the due date for the lab because we just finished the qualitative analysis Tuesday. So I guess it officially would be due next Tuesday, but that's too late for me because I got to get the grades done. And so I need the labs by Monday. It'd be nice to get the labs done earlier, but I usually just grade all the labs once I get those in. And so I'll probably start working on the quizzes. Hopefully you guys turn in the quizzes if you're missing any. And then I can start working on grading those. And then I'm gonna give you your exams back right after class. I just need to scan those in and then I'll get them back to you today. But were there any questions? The final exam is going to be due the same. The final exam I'm going to give you on tomorrow, and then we'll just have it due Monday. Final exam. Final exam is not going to be that much longer, I think. I haven't figured it out. Well, I guess I could make it like twice as long, twice the normal. It's worth twice as many points. Does that work for you guys? I don't know what your schedule is if you're headed out. Yeah. Tomorrow's optional session. I mean, I'm done through chapter 19. So tomorrow we can have a session. Just if you have questions, you know, it's just like if you have some questions about earlier material, we can cover that. But if there are no questions, then you know, call it early. But tomorrow I do have one more lab I wanted to do. And so tomorrow's session is going to be the redox, but the redox is just some demonstrations of redox reactions. That's it. And so you're just going to write the equations. And so there's one more lab report that's going to be for tomorrow, but basically I'm going to write all the equations and you just have to copy them down and then turn that in with some observations. That's it. Tomorrow's lab is not, tomorrow's lab is just, it's a regular, we'll do the lab right at the beginning. And so I'll just do, I'm not going to do a full 3 hours worth of reactions. We'll just do like an hour's worth. We still need the nomenclature. The nomenclature I'll throw on the final. And so there's going to be a nomenclature thing to make up for the nomenclature thing that we had the other time. Tomorrow, I'm going to upload the exam onto Piazza.
There's no way that you could upload it tonight?
Unfortunately not tonight because I haven't completed the final exam yet. And so
Okay.
I need to finish writing the final. Charles Law, what about trial 2 of Charles Law? Yeah, I mean, I did trial 1. All you have to do is essentially copy it, except you got to use the numbers for trial 2, you know, and then make the graph for trial 2. And so you have the template there. It's just essentially changing the numbers and then using the same equations. So trial 2, it should have been very easy, in fact, except, you know, the graph, it'll take a little bit of time to do the calculations on graph, but I did everything for you guys. So it's just a matter of, maybe I made it too easy, you know, things, because it's not going to be quite that easy in Chem 1A. Yeah, I'm going to put the extra credit nomenclature on the final. Let's do it then. So extra credit nomenclature will be on the final. I was going to make it a Canvas, but a Canvas quiz. I decided not to. We have lab. We have a lab. If you look at the syllabus here, we have one more lab to do. Oh, actually, I was supposed to do that today. I forgot. I thought it was tomorrow. And lab checkout is easy, so I'm not going to talk about that. But there's one more experiment, experiment 13, that I want to do right at the beginning. Since it is our final exam day, you know, this won't take long to do. And so just come in at the beginning and then just copy the reactions off. And if there are questions, this was, when I did this was thinking I was going to have in-class exams, not take home. But since I'm having take home, then do it. Yeah, you have to join tomorrow for the lab, experiment 13. This is supposed to, maybe there's enough time today. Do you want to do the lab today? We could do it today. Okay, we'll do the lab today. So what I'm going to do is I'm going to move back to the lab. And then, so we'll take a break here for like 15 or 20 minutes, and then we'll do the lab. It'll be a short lab. We'll just look at some redox reactions, although we did some redox reactions in the other one. We'll take a look at some redox reactions now. Let me take a look at the lab here. Okay, it's experiment 12 is oxidation reduction in your lab notebook. These are just entered. Actually, they changed this lab. All right, this is different than the lab I do. I usually have a little bit more redox. These are the redox ones I was planning to do as a demo, which is iron 2 sulfate and silver nitrate, potassium dichromate, sulfuric acid, and oxalic acid. How about this then? We'll just make a prediction of what's going to happen. Why don't you tell me what's going to happen here for 1 and 2? We'll just do 1, 2, and let's see. Should we do 3? Iron 2 sulfate, sodium hydroxide. No, that's not the one I wanted here. Okay, this is what we could do. Instead of the lab, I'll break you guys up and then you can just tell me what you predict. Potassium dichromate, we saw what that stuff looks like. It's kind of an orange colored solution and we used some before. It's a great oxidizing agent. Then we had some sulfuric acid, H2SO4. And then we had, in this case, we're going to have oxalic acid, H2C2O4. And then predict the products. So in this particular reaction here, number 2, I'll give you a hint. A CCG is produced, clear colorless gas. And so this will start to bubble. CCG is produced. So what we use for this method is the chart/skeleton. Let me see if that reaction is on YouTube. Oh, I won't have to do it. So this is going to qualify as a lab. The lab is this is lab, so this is going to be 10 points. We'll make it easy. You have an hour to figure it out. Okay, so just go ahead and try to predict this. I'm going to break you up into groups. You can work in groups for this. I got 16. We'll break it up into four-person groups. Yeah. Yeah, actually, let's break up the points. We'll do 1 and 2. Can you do, or how long do you think this will take you? 1 and 2, you'll have 30 minutes each to figure it out. Number 1, this is reaction number 2. Number 1 is iron 2 sulfate and silver nitrate. There's also water, of course, there's water in all of these, plus H2O, so this is an additional hint here. All right, let me see. And if you have requests for the group, let me know. Otherwise, it made the group here. Anthony Moniza, Carlos. Is Carlos here? Okay, I think I got it. I can move it around as well. And so we'll go with this. And so this will be the redox lab. It's going to be totally dry lab. I might tape these reactions, but maybe not. Actually, I'm going to skip the demo part. Just work on this here. And so this will be the final lab this semester. It's going to be predictions. Reaction 1 and reaction 2. All right, try to predict the driving force as well.